In the last video of this lecture, I want to follow up on two quick things from the previous video. So the first question is when we can take semidirect products of the same two groups, H and K, with respect to different homomorphisms phi, and get groups that are isomorphic. So in the last video, we talked about an exercise from section 5.5 of Dummett and Foote. It's closely related to this lemma 6.2 in Conrad's semidirect products notes, which says that if F is an automorphism of K, so F from K to K is an automorphism, what does that mean? Well, that means whenever you have phi from K to odd H, a homomorphism, you also have another homomorphism that is phi following F. So you do the automorphism first, and then you apply the homomorphism. So that's also a homomorphism from K to odd H. And the semidirect products that you get are isomorphic. The semidirect product of H and K with respect to phi following F is the same, is isomorphic to the semidirect product of H and K with respect to phi. And the proof of this is an exercise. You should think about how this is related to the exercise you proved for homework. The setup's not exactly the same. In that exercise, you assumed that K is a cyclic group and that the image of the two different homomorphisms, phi1 and phi2, from K to odd H were conjugate subgroups in odd H. So these aren't the same result exactly, but they definitely exist in the same universe. OK, so what did we see when classifying groups of order PQ? We saw that when P less than Q are primes and Q is 1 mod P, that there is one non-abelian group of order PQ up to isomorphism. And the question is, what is it? Like, how do you think about it? So we know that it is the semidirect product of Z mod QZ and Z mod PZ with respect to any non-trivial homomorphism from Z mod PZ to aught Z mod QZ. But what's a good concrete way to think about the elements? So here's the one that I like. We know the affine group over Z mod QZ is the set of 2 by 2 matrices x, y, 0, 1, where x is in Z mod QZ star and y is in Z mod QZ. We saw how to think of this group as a semidirect product earlier. The order of this group, well, there's q minus 1 choices for x and q choices for y. It's q times q minus 1. Let's define APQ to be the subset of matrices x, y, 0, 1, where x to the p is equal to the identity in Z mod QZ star. So let me really emphasize in Z mod QZ star. So what does that mean about x? So x to the p is 1, which doesn't mean that the order of x is p. It means the order of x divides p. So x is an element of order dividing p in Z mod QZ star. It could be the identity. But that means that x is in the unique subgroup of order p in Z mod QZ star. And now we're using the fact that we know that Z mod QZ star is a cyclic group of order q minus 1. So it has a unique subgroup of order p. So in particular, how many choices do we have now for x? We have exactly p choices. So it's a little exercise to show that, in fact, APQ is a subgroup of this affine group over Z mod QZ, and that it's non-abelian. And we see that the order is p times q.